So another application is looking at rates of change, and a lot of situations deal with rate of change. Here we have an example of bacteria, and it is growing according to the following equation. What your derivative can tell you is it can give you an estimate how fast something is growing at a specific time. Because if we're finding that instantaneous rate of change, we know at 10 hours how fast it's growing. And we can find out how fast it would be growing after 20 hours. And that can give us some sort of indication of, is there going to be a problem with this later on, or what's going to happen later on based on this model. So again, anytime you're looking at the rate of growth, you're trying to find out how much it's growing per hour. And anytime you're doing a growing per hour, that's going to be a derivative. So if we find the derivative of this function and then plug it in, we can estimate that after 10 hours, it would be growing at a rate of about 75 bacteria per hour. Now, can we use calculus to show that it's always going to increase? You might be able to say, well, I know from my equation, it's a parabola that keeps going up forever. It's always increasing. But we can also, if we take our derivative and we think about our first derivative test, we can make our derivative equal to 0, and we'd find out at t equals negative 2.5, it's equal to 0. Because it's a parabola, we know that that's going to be a local minimum. And because it's a parabola, we already know it's decreasing before and increasing after. But if we would do our first derivative test and plug in negative 2.5 and check a value in our derivative before that, we'd see that it's decreasing. And after that, we'd see that it's increasing. And since our critical value happened at negative 2.5, and we're thinking of time greater than or equal to 0, this function is always increasing. And it's not really realistic because you can't, have bacteria, and eventually something happens. They run out of food, and this is where, different types of mathematics like chaos theory comes in, because it can follow a model for a certain time and then something bad happens. They run out of food and then the population enters into a period of chaos for a bit till it stabilizes and can start that model again. I don't know why someone would want a controlled laboratory experiment where they grew mosquitoes. But if you did, and you found that population equation, you could find the growth rate of mosquitoes after 5 days. So again, the key words that we're looking at here is a rate, growth rate. And if they're asking for a growth rate, they're asking for mosquitoes per day. And so we could take the derivative. And we got a chain rule here. Again, the derivative of e stays the same, but then we have a chain rule, so we'd have to multiply by 0.09. Plug in 5. This would be a calculator question. And so that growth rate is approximately 35 mosquitoes per day. Here would be an example where it's okay not to go to 3 sig figs, because that 0.3 of mosquito, How do mosquitoes hatch? From eggs? So 0.3 of the mosquitoes out of the egg and the rest of the mosquitoes still in the egg. So that's how you could get 35.3, maybe? Maybe. So often in these rate of change problems, they give you the equation. So here again, we've got a temperature equation. Time is in minutes, and we can find the rate of change of the temperature. So here is the hint that's letting you know I should do the derivative. How fast is the temperature changing per minute at that time? So we can find the derivative. And plug the value of 10 at that time. And here again, the negative means that it's decreasing in temperature. It's going down 2.44 degrees every minute. I'll put up the answer for the first one here so you can see how you did. So each time here, because it's months, means February is 2, March, April, May would be 5, and so on. So May 1st, you'd plug in 5. Now you would just go into the actual equation because you're just finding the population. What's the rate of change? This is where you do your derivative. And now what does that mean? That means that that deer population is increasing at a rate of change of 104 deer per month on that date. So on that date in particular, that's what the current trend is. So you would predict how much there would be on June 1st based on that. And again, there's some practice questions at the bottom that you can try.